So what we've done so far is we learned about enzyme commission classes, and then we used the RCSB API to download a number of ligand molecules. We just picked one ligand, and you might say, why did we pick that ligand? We just picked one just because we liked it, but you could have picked another one. We made some modifications to it that we think would be interesting, and now we're going to try taking all three of those ligands, the original one and the two that we modified, and kind of see how that affects docking to our trypsin protein. If you were doing this kind of like a study for research, you might have a sort of intermediary step in between picking the ligand and doing the modification. You might like go ahead and just look at the interactions that exist for that ligand. If you're interested in how you would do that, so we're kind of skipping a step, but if you're interested in how you would do that, there is a notebook that shows kind of like looking at how the ideal structure is bound to the ligand in this extras folder, if you're curious. So we kind of just went from just picking out the ligand to docking it, not to docking it, to modifying it, but you might look at it before you do that. So now that we have our three modified ligands, we're going to start getting ready to actually do our docking calculation. And we are going to be doing docking with a Python API to a program called AutoDocVina. And AutoDocVina is very nice because it's open source, meaning that it's free. Well, that doesn't mean that it's free, but it's free and open source. It also has a Python API so that we can work with it in Jupyter Notebooks. So to get started and to get ready for doing our docking calculation, we're going to have to make sure that we have our structures in the particular format that AutoDocVina wants us to have them in. So that's what we're going to be doing in this docking preparation notebook. So if you want to follow along, I am now in this notebook called Docking Preparation, and you can just double click and open that. So the questions here are, how do I prepare structure files for docking? We're going to use, what we're going to be doing is we're going to be using the RCSB search API to find our protein structure. So in order to do docking, we're going to need a protein structure to dock to. We don't have that yet. And we're also going to be doing several steps to actually prepare our structures. So in this notebook, we're going to be downloading a trypsin protein structure with our ligand of interest already docked to it, and that's going to help us identify the binding pocket that we're docking. We're going to isolate the protein structure. That means that when it comes from the PDB, it's going to have things like other ligands attached. It might have water molecules attached to it. We're going to use some Python program to get rid of those extra molecules on the protein. Then we're going to need to add hydrogens to our protein. We're also going to need to make sure that it doesn't have any missing atoms. So we're going to use another program to do that, as well as adjust it to a particular pH. And then finally, we're going to be creating a file called a PDBQT file. And the PDBQT file is a special molecular file format that is used by AutoDocVina and other AutoDoc tools. So you may see PDBQT, it's pretty much always used with AutoDoc. It is very similar to a PDB file, except that it has some additional information needed for docking programs. Okay, so again, going over our Python libraries, we've already used the RCSB search API. We used that in the first notebook. We're going to be using requests again to do our download. OS is what we've been using to create our folders. And then we're going to be adding some new software in this notebook, notably NGLView for doing molecular visualization. And we're also going to be working with a library called MDAnalysis. So MDAnalysis is an open source Python library that's very commonly used to do calculations from molecular dynamic simulations. But we're going to be using something called their selection syntax language to isolate particular parts of our molecules, as well as their ability to read and write from various molecular file formats. We're also going to be adding some command line software in this notebook. We're going to be using a software called PDB to PQR. And this software is capable of checking our protein for missing atoms in our residue, as well as adjusting hydrogens for a particular pH. And then we're going to be using another command line utility called Meeko that's going to put our ligands, it's going to convert our ligands from SDF to PDBQT. So this is a lot of different software steps that we're using, but ultimately where we're going is getting those PDBQT files that are input for docking to AutoDock-Vena. And we want to make sure here we're using like specialized libraries, especially for things like docking and proteins. Okay, so in order to do our docking calculation, we are going to need a structure to dock to. So we're going to need our protein structure. And so far we have a ligand, but we don't have trypsin. So we need to get that trypsin. And we again are going to use hopefully the RCSB search API in order to get that. So this is very similar to the first notebook. We're importing this to do our search. We have a different import here called text query. So we're going to have a different query. We're going to actually just query for our ligand name. So I'm going to go down here where it says Q2, fill in text query here. And I'm going to type text query and then open parentheses, and I'm going to put the name of my ligand, 13 capital U in quotes and close parentheses. So we're doing another query to the PDB. Again, we're querying for trypsins. This is very similar to the first notebook, but now we're querying for trypsins that have this ligand attached. So let's execute that cell and we'll see if it runs. Okay, mine ran okay. I don't know, I hope I'm not checking the Discord now, but it's very possible that we're gonna have the problem again where, everyone's running at the same time. But what I can see is it's telling me that my PDB ID that it's finding that has 13U and a trypsin is 2ZQ2. So I could rcsb.org. I just want to show you that in the web browser just so we can look at it. 2ZQ2. So if we look at, so you wouldn't necessarily have to look at this. I just want to show you that what you're getting in your notebook corresponds to something that's on the PDB. So we did that search just from our Jupyter notebook, and we found this structure, 2ZQ2. And we can see that this is telling us that this is a structure that's exploring the trypsin S3 pocket. And so we have a trypsin here. And then if you scroll down, it's going to tell us what macromolecules we have. We have cationic trypsin. And then you can also see on this page that indeed we do have our ligand attached. Here is a section on small molecules that are in this ligand. We have 13U. And there are also some other small molecules attached. So there's glycerol and also calcium ions in this structure. So we did our search. We could have just trusted that without checking it on the PDB, but there it is. So this has returned a list to us. If there was more than one structure that had trypsin and that ligand, then we would have gotten a list with multiple structures. We're just going to get a single PDB ID here. We only have one, so we're just going to grab that one, and we're going to set our PDB ID equal to results. We're going to index into that list and get the first one. There is only one. And then I'm going to do this just because I like how it looks better, but this is going to change all of my letters to lowercase. So I'm just getting the first entry, 2ZQ2, and I'm changing it to lowercase. And then I can see what my PDB ID is. So far we have just the PDB ID. Now we actually want to get the structure. So again, we're going to be just like for the ligands on the step that many of us were unfortunately not able to complete. We are going to use the PDB API to download that structure directly into our Jupyter notebook. So here we have our imports again. We import OS and request because request is what we use to actually download that file. We are going to make a directory called the protein structures. And here is another part that we need to fill in. We need to fill in the function to actually make the directory. So here we're going to use os.make dirs. And I'm going to tell it the protein directory. I made a variable here called protein directory. And I'm going to say exist OK equals true. This is just so I can run it over and over again if I need to. So here I am going, this step is going to make a folder on my local computer called protein structures. And then here I'm going to actually call the PDB API to get that structure. So I'm saying files rcsb.org download. I'm giving that PDB ID that we found in our search. And then if everything goes according to plan, it should print 200 here for that status code working. So that tells me that I retrieved the file. And then I'm going to save it. This is how we're actually saving it. I'm going to fill in pdb request.text. And I'm going to go ahead and execute that. So this step that we just did so far, where we use the PDB API, found our ID, and then did a request and filled it in. We're just showing you this because, you can use the Jupyter Notebook to do this. If you want, if you're doing this kind of calculations, you can totally just program it in without ever taking your browser to the PDB website, and you can download this stuff and you can save it. If you didn't want to do it this way, of course, it would be totally fine for you to go to this page and press the download button on this structure and download. So essentially, we're using Python programming to do the same thing that you would do if you went to this page and clicked download files PDB format. We're just using Python to do it here. So if that works, yes.
Can you make your text a little bigger?
Yes. Is that okay? So if that works, you should now have this directory called protein structures. And in protein structures, you'll have 2zq2.pdb. And if you wanted, you could look at it, and it's going to be the PDB. It's going to be the actual text file for the PDB structure that you downloaded. So that's just a nice way for us to get that without having to go to the graphical interface. Okay, so now that we have downloaded our protein structure, let's actually take some time to visualize it. So I think that this is something that's very common. People want to download their structure. They kind of want to see what it looks like. In order to visualize it, we're going to be using a combination of libraries. We're going to be using a library called MDAnalysis in order to load our structure. And then we're going to be using a library called NGLView that works very nicely with MDAnalysis in order to see it. So we will load it into into a data structure that is specific to MDAnalysis called a universe. So when you use MDAnalysis, it's just a terminology that they use. They call a molecular system a universe. So that's just something about the way the MDAnalysis library works. So to load in a particular file, we'll do MDA. So we here imported MDAnalysis as MDA. So when we want to load a structure, we'll do MDA.universe. And then in universe, we are going to put the file that we would like to load. I'm going to be using variables here in my file name. So I am going to do F and then open and close quotes for my string. And then my file is in my protein structure directory, and it has the pdbid.pdb as the file name. So I'm using curly brackets and then protein structure. Protein directory. That's the name of the variable we're using. / and then our PDB ID .pdb. So this is just a way that I'm using variables in my file name. Okay, and so if I run that, I should see an output. It tells me that I have loaded an in the analysis universe, and it tells me that my universe has 2024 atoms, which is a great number because that is the year it currently is. But this just tells me that I have loaded a molecular structure with 2024 atoms. Okay, so I've loaded that in. Now I can want to actually see what it looks like. And now I'm going to use a library called NGLView to see what my universe looks like. So here I'm going to create a view and set it equal to nv.show ND analysis. And then I'm going to give it that ND analysis universe I created in the previous cell. And then if I type the name of that view that in the last as the last thing in the cell, I'm going to see a nice molecular structure once this runs. Okay, so this is the structure that I've downloaded from the PDB. This is like what my trypsin looks like. It's kind of hard to see here, but we have a number of water molecules attached to this as well as small molecules. We can rotate the structure by clicking and dragging. You can zoom in by using the scroll wheel on your mouse if you have one. And we can see that also when you hover over different atoms, it will give you some information about those structures. So that's all very nice, but we might want to make our view of this structure a little bit prettier. So we might want to kind of view things, you know, be able to see the water molecules or see where the ligand is bound. And we are going to use MD analysis and NGLView to make this view a little bit nicer. So MD analysis, one thing that's pretty nice about it is it has this selection syntax that lets you select different parts of your MD analysis universe or different parts of your molecule. So here we're using that analysis, that MD analysis universe, and then a method called select atoms. So here I'm creating a variable called protein where I'm selecting the protein atoms. Here I'm selecting the ligand. So our ligand name is 13U. And so all of the atoms associated with the ligand are labeled with the residue name 13U. And then if we want to select water, we can do u.select atoms. And we'll fill in res name HOH because that is the name of water residues in our structure. Okay, once I fill that in, I can execute that code. And here I've put water as the last thing in the cell. So here it's telling me about what is in that atom group. And it tells me that water is an atom group with 269 atoms. So after we've selected these different parts of the structure, we've selected the protein, the ligand, and the water, we can use NGLView to add representations to just particular parts. So here in this next cell, we're creating a better visualization of our protein and ligand structure. And this is all just informational so that we can have an idea of what we're trying to do. But here we're starting with show MD analysis for the protein. I'm clearing the representation just so I can make it look the way I want. And I think that I want to see my protein with I want to add the representation to be the surface area. And I want to color that surface area by hydrophobicity just to give me some information about that protein and where the ligand is bound. So is there anything that we can see about that? So to add the representation for surface and hydrophobicity, we're going to do view.add representation. We'll fill in surface here. And then I'm going to say color scheme equals hydrophobicity. And if you're interested in like sort of how we know what to fill in here and different things that you can view using NGL view, then we do have in our first Python scripting crash course, we had a lesson just on using NGL view and filling in representations. So again, I'm just adding this line where I add a surface representation and I color by hydrophobicity. And then I'm adding my ligand. So I'm adding my ligand as another component in the view. I'm giving it ball and stick representation. Then I'm adding the water into my view and making it have the representation space fill. So let's take a look at what this comes to. Okay, scrolling. Whoop. All right, there we go. So that's our view. So this is a nicer view of our protein. We can see that we have the structure of the protein. The green areas are hydrophilic. Areas that are more red are hydrophobic. These little balls on the surface, those are the water molecules that are part of the protein structure. Where our ligand is if we actually have to drag our protein around to the other side. So if you look on the bottom, you're going to see that we have the ligand bound here in this spot. And I just used click and drag to kind of pan the image, but we can kind of zoom in here. And so here is our ligand. You might notice that it kind of looks like we have two ligands bound. But one thing that we can see is that this ligand is kind of on this hydrophobic area on the surface. And then also we can get a view of sort of where this is. So we kind of see that this ligand is kind of going really deep into this binding pocket. So this is just the structure that comes out of the PDB. So you may be wondering, when you look at this, you may be wondering, why do I see two ligands here when only one is bound? So here, on viewing this structure, you'll notice that our ligand seems to appear twice. And we can actually investigate that. So if you look at the text files, if you look at the PDB that you downloaded from the protein data bank in a text editor instead of in this, what we'll see is that for this particular structure, we have alternate locations for our ligand. So if you look, let's take this one for example. We have 501. This is actually the same atom repeated. Wait, is that the same atom? Maybe one of these. Same atom repeated twice. You'll notice for each atom we have something marked with A and something marked with B. And what this means is that in the experimental structure, there were two alternate locations for the ligand. And so we can, I'm not sure it tells you, so it does tell you here, so that's A and this is B, and you can see this kind of on the end of the label here. But really there's just one ligand, it just binds kind of to the surface in two ways. So MD analysis luckily has a way, if we wanted to just select one particular location of our ligand, we could alter that selection syntax and just do res name and alt lock A or alt lock B if we just wanted to select one or the other. So we really don't want those alternate locations in our structure when we do the docking. We don't need the ligand, but if you were to examine the protein, it's hard to see, but we actually have alternate location for some of the protein residues as well. So we're just still on our way to getting ready to, we're still on our way to making our structure. But what we need to do is we've examined it. We need to save just the PDB file with just our protein in it, and that's what we're going to ultimately put into autodock Vina for our docking calculation. So you'll recall from earlier that we created a variable. Just 1 minute. You'll recall from earlier that we created a variable. I'm just going to scroll up. You'll recall from earlier that we created a variable called protein, and we set that equal to our universe, and we selected just the protein atoms. So in this cell, after we've examined it, we are going to use MD analysis to write a PDB that contains our protein only. So this does not have our ligand in it or any of the other small molecules that are bound to the structure. It just has our protein. And we're saving this in our protein directory, so our protein structures directory. And you'll see that here we're giving it a new name. We're calling it protein_PDBID.PDB. Okay, so we do get a warning here from MD analysis. It's going to tell us there's no information found for formal charges. And so it's just going to tell us, MD analysis is telling us, hey, there's no charge information set on this structure. So it's just MD analysis giving a warning to us about that. But that's actually totally fine for our purposes. We can just kind of ignore this warning because we don't need charges to be set. Okay, so now that we have, and once you do that, if you look in your protein structures folder, you're going to see a file just called protein_2ZQ2. So that is just the structure that we saved, and we'll be moving on from that. So now that we have that
Jessica?
structure, yes.
There's been a few requests to slow down just a bit and recap what we've done up to this point.
Okay. Do you have any idea of where we need to go?
Maybe just a slow walkthrough of what each of the steps did is probably just run through what each of the blocks did. Don't necessarily like repeat everything, just what we did up to this point, I think should help.
Okay, so we did a search from the PDB API to get our protein structure. That's what we did here. And then we downloaded it. And then the next part was loading our structure into an MD analysis universe. And then we just looked at this with NGL view. So here we're loading our structure into an MD analysis universe. We use show MD analysis. And we get this structure. And then we select different parts of our structure. So here we're using MD analysis to select our protein, our residue, and our water. And then we are just making a nice view of our protein structure where we're covering the surface, where we're coloring the surface by hydrophobicity and looking at where our ligand is bound. If there are specific questions, I'd be happy to answer those. Okay, I see a question asking about why there are two ligands. This is an artifact of protein data bank structures. So these are experimentally determined structures. A lot of times they're determined with X-ray diffraction. And sometimes there might be two locations that the ligand are likely to bind. So this is just a result of that. So right now we are looking at the experimentally determined structure. This is before we're doing any docking, but this is the experimentally determined structure for this ligand. If you are wondering how we know hydrophilic versus hydrophobic, to me, that makes sense that the red is hydrophobic, but you can also check the documentation for NGL view. Okay, so this is just a note. If you wanted to select one of the alternate locations instead of the other, MD Analysis has the ability to do that by altering your selection statement. Okay, and then what we did here was we just wrote our PDB file to a new file. And we had a question. So here we only really have one docking location. This is the docking location. It's just that we have two different ways the ligand is bound in the experimentally determined structure. Okay, so in this last step, we saved a protein file in our directory. So again, this file that we've saved contains the protein structure only. And the structure that is present on the protein data bank, we have those ligands bound already. And we also have things like waters and other small molecules. In order to do our docking calculation, we do not want those present in the structure that we give to AutoDocVina. So we use MD Analysis to get the protein only. Okay, so now that we have the protein structure, there's a little bit more, we have that isolated, but there is a little bit more work that we need to do in order to prepare this structure for docking. When you get structures out of the protein data bank, they are not going to have hydrogens added typically. So typically all the structures that come from the protein data bank have your heavy atoms only. They do not have hydrogens added. In order to do docking, we're going to want to add those hydrogens, and the hydrogens also, the proteins also need to be adjusted so that the hydrogens correspond to particular protonation states or pHs. So we are going to now run a program called PDB2PQR. It's going to do a few things for us. It is going to go through our protein structure and check for missing heavy atoms. So sometimes when you have a structure from the protein data bank, you might be missing some heavy atoms. Sometimes you might be missing more than just a few heavy atoms. You could be missing loops. But we're going to have something that adds the heavy atoms in that are missing for us. It's also going to add hydrogens for us to adjust to a particular pH and also make sure that we have hydrogens attached. And then this program is also going to calculate partial charges for our protein. We don't necessarily need those because the scoring function that we're using with AutoDocVina does not end up using the charges. But just for the sake of completeness, we are going to save them in case we wanted to do something where it mattered. So we are using a program called PDB2PQR. Another program that you'll see often used in this kind of thing is called a PDB fixer. It's an open source tool developed by OpenMM, and it's designed to fix common problems in PDB files. So that's something else that you might see used. And to see an example, if you want to see an example of using PDB fixer, I have included a link to a recent YouTube video posted by the Open Force Field Initiative. So just in ours, we're going to use a command line program called PDB2PQR. And to use that, this is a command line program. So this is not a Python script. This is not a Python script. We have PDB2PQR. We're doing, here we're setting what we want our output file to be. And we're setting it equal to protein structures and protein h.pdb. We want to adjust to pH 7.4. So we are taking in our PDB file that we wrote previously, and it's also writing out a PQR file. And again, this is not a Python program. This is a command line tool. So if you were running in an environment where you had a terminal, you could run this command in the terminal. And the way that we run command line programs in Jupyter Notebooks is we add an exclamation point to the front. So I'm going to click inside of that cell and press Shift Enter. And so this is PDB to PQR running. You can see that it has some citations for you as well as some outputs. So here it tells us that it's creating a biomolecule object. It's telling us places where we discuss the idea of multiple occupancies in our PDB file. So we have some residues that have atoms with multiple occupancies. And PDB to PQR is picking some of these. It also is telling us that there are some missing atoms that have been found. And then is outputting a file for us. Okay, so this PDB to PQR program is going to output two files. It's going to output a PDB file and a PQR file. So this PDB file is similar to PDB files we've worked with before, except that it now contains hydrogens. And the PQR file is another molecular file format. So again, we did want to use this because this is a specialized program for proteins. But now that we have that and we have our hydrogens, we want to actually convert to a PDBQT file that is input for AutoDocVina. So for use with AutoDocVina, we need that PDB to PQR file format. So this next step is going to take us from the output from PDB to PQR to PDBQT. Okay. So we're going to make yet another directory that's just going to contain our actual PDBQT files. So in quotes, we're going to put PDBQT. So we're making another directory called PDBQT. And then we're using MD analysis to read in that PQR file that we created in a previous step and output it to PDBQT format. Okay, so now we have a PDB file generated by MD analysis. And I just found so you could have also used a program called OpenBabel for this. And we had that at first, but just to limit the number of libraries that we're using for this workshop, we're sticking with MD analysis. This next cell just makes some small adjustment to our PDBQT file so that it's good to read with AutoDocVina. So we can just execute this cell so that our file is good to go. So now, after this step, we have a folder called PDBQT. We have our protein structure as a PDBQT file. So this is ready for us to input as a receptor with AutoDocVina. Okay, so the last thing before we do docking, we need to actually prepare our ligand files. So when we're inputting our ligands to AutoDocVina, we want to make sure that we have a 3D structure and that we also have our hydrogens added. We have already taken care of having a 3-dimensional structure because we pulled our ideal structure from the PDB itself. So we have that ideal 3D structure already. For the ligands that we modified, we took that ideal structure and made modifications to it and then did a refinement using RDKit. So we have our 3D structure ready to go. And then we also have hydrogens added already. We did that with RDKit as well. So the last thing that we need to do is to take these from an SDF format and convert them to that special PDBQT file format that we need for docking. And so to do that part, we are going to use a special command line program called Meeko. And Meeko is another program that is specialized for performing docking calculations. And particularly docking calculations, it can be used to make PDBQT files for small molecules. So we have to use one thing to do our protein for our large molecule for our protein. And then we use a different program to prepare our small molecules because these programs have different focuses. And so you could have used, like, say, something different to prepare your PDBQT for docking, something different than Meeko. But we're going to see that using Meeko is going to allow us to nicely visualize our docking results using a different library. So that's our reasoning for using this one. And so to prepare our small molecules, we're using a command line utility. It's something called MK prepare ligand. We're putting in the notebook that Paul went over with you where we modified our ligands, we saved some structures as SDF in our ligands to doc folder. So we're inputting ligands to doc 13u.sdf. This is our unmodified ligands. Then we're going to save it in our PDBQT folder as 13u.pdbqt. We do the same thing for this modified methyl. We're going to read in the one that we modified with a methyl group and output it as a PDBQT. And then here you need to add in one more command. So do MK prepare ligands so that we can prepare our ligand that was modified with a methyl group. We'll do ligands to doc 13u modified in.sdf. So that was the name that we gave the file previously. And then we're going to output it as PDBQT 13u modified in.pdbqt. Okay, and we can run that cell. May take a moment. But now we have, if we check our PDBQT folder, we will have our protein structure as a PDBQT. We have our original ligand as a PDBQT. Then we have our ligand modified with a methyl ligand as a PDBQT, and our ligand modified with the nitrogen as a PDBQT. So whenever you do calculations with AutoDocVina, you'll have to do this step where you take your protein structure and you make sure you add your hydrogens, and the same thing with your ligands to get that starting PDBQT file. All right, I will pause here and we can take a few questions if anyone wants to give me a few from the Discord, or if there's any part that people need to see.
Jessica, there's a question here. PDB to PQR is not recognized as an internal or external command. Operable program or batch file. How should I parse this problem?
Do you have the exclamation mark in front of your PDB to PQR command? And make sure, so if you are running on either KimCompute or CodeSpaces, this should work. If you installed on your own personal computer, you may need to make sure your environment is activated if you didn't, and you have to make sure that it's actually installed. But this is definitely installed on both KimCompute and CodeSpaces. So we've had a question about two amino acids in the same place for rotamers. I don't directly know the answer to that, but it's very possible that you may need to use something like PDB fixer. So there are, if you would like, there is a link to PDB fixer for some more. That's really for more intense changes that need to be made to the PDB. Okay, so there is no exercise at the end of this notebook actually, but let's take about a 10-minute break. And then when we come back, we will do our final docking calculation. Sound good, Paul? Okay, Paul said sounds good. All right, we will take a 10-minute break. Please continue to ask questions in the Discord if you have them. I'm going to step away for a moment. Okay, we'll get started again in a minute or two. All right, we are ready to dock, I think. So finally, we're getting to the step where we're actually going to perform a docking calculation. So those of you who have done any kind of calculation like this before, maybe you do molecular dynamics simulations, or maybe even if you do docking simulations. And this is just me remarking on what we did in this last notebook. What we did in this last notebook, we did a lot, and we had to think a lot about what our hydrogens were, what file formats we were reading in, what file formats we were writing out. And if you do these kind of calculations, you may feel like you spend a lot of time doing structure preparation. You probably do feel like that. Like there's a ton of time that you're going to spend thinking about your files and the information for your files. And then, that's a very difficult part of doing this kind of work is preparing your input files. And so that's just a note. And I'm sure that those of you who have done these kind of calculations before definitely know that. So we did the part where we have prepared our input files, and now we are actually ready to perform the docking calculation itself.